All right, let's pick up with example 4 in lesson 9.1. Let's read this together. Biology connection. The table compares the wing flapping rate R in beats per second to the wing length L in centimeters for several birds. Do the data show an inverse variation? If so, find a model for the relationship between R and L. All right, so R is what? R is flapping rate. Okay, so flapping rate. And L is wing length. All right, now let's take a look at this table that on example 4 on page 539, 535. So it says carrion crow, beats per second, and then is 3.6, and the length is 32.5. Okay, so remember, again, we have some sort of variation. They're not really too clear in here about how they vary. I don't think it matters too much whether you say R equals K divided by L, or you flip it around and say L equals K divided by R. Both of these guys are equivalent statements, okay? So either way, though, what's K going to equal? Well, K is going to equal R times L. So take your calculators out and start multiplying these out. So if we multiply 3.6, I'm looking at the first one, times 32.5, I end up with 117. Okay, 117. So write that down. Now, the common scoter is 5 times 23.5. 117.5. Yeah, that's still in the neighborhood. Doesn't have to be perfectly on the money. It's just going to be in the neighborhood. All right, great crested grebe, 6.3 times 18.7. What's that? 117.81, and so on and so forth. So you go through that, and you're gonna be roughly all about the same thing. So what they tend to do is they take all those and they get the average of all of those K's, which are all in the neighborhood together. And they're saying, well, on average, K is going to equal 117. So you're going to set up your inverse variation based on that. In the example, they're saying R equals 117 over S, not S, what is it, L. L. And again, you could just as easily have said length equals 117 over R. Either one of those is correct, right? Because they're both going to be inverses no matter what. All right, so let's flip the page. Okay, so we're now on page 536. And we're looking at goal 2, using joint variation. Okay, so we've just covered inverse variation. Now we're going to do joint variation, which is very similar to direct variation, except more than one, and it could be also an inverse variation. I shouldn't say that. It could be a mixture of those, but it's more than one variable is involved. So let's read the definition of joint variation. Joint variation occurs when a quantity varies directly as the product of two or more other quantities. For instance, if Z equals, we still have a constant of variation in there, K, X, Y. So this is all going to be direct, okay, where K is not equal to 0, okay, because otherwise there'd be no variation at all. When Z varies jointly with X and Y, other types of variation are also possible, as illustrated in the following example. Okay, so it's just now that you have two variables, X and Y, that are going to vary jointly with Z, okay? All right, example 5. Says, write an equation for the given relationship. Y varies directly with X. Okay, so if Y varies directly with X, remember that's just direct variation. Y equals KX. All right, let's look at B. We'll read that together. B, Y varies inversely with X. Okay, that's what you just learned. So Y equals K divided by X. All right, let's look at C. C, Z varies jointly with X and Y. So Z equals KXY. And this is like the situation what we were talking about with this is a joint variation right here. Okay, D, Y varies inversely with the square of X. So Y equals, if it's inverse, that means, it's going to be over here, and it's the square of X. So we're talking about X squared. Okay, and then last one, E, says Z varies directly with Y and inversely with X. So, it's pretty much the way you would expect it to be. So you got a direct variation going on with Y, so that's K, Y, but inverse with X. So X is going to be here on the bottom. And that's pretty much it. So you're translating listening to these different sentences in English and translating them into the appropriate type of variation based on what they're saying there. Okay, now let's look at example 6, and that's our last example. Oops, I still got my eraser on. Example 6. Okay, let's read it together. The law of universal gravitation states that the gravitational F in force in newtons, okay, so this is F, this is force in newtons, okay, based on Sir Isaac Newton. He came up with that unit of measurement between two objects varies jointly with their masses, okay, masses, M1 and M2, in kilograms, okay, so this is going to be in kilograms as your unit. And inversely, so this is directly with this, and inversely, with the square of the distance d in meters, so d squared in meters between the distance between the two objects. All right. The constant of variation is noted by G, which has to do with gravity. This is the universal gravitational constant. It's based on living on Earth here. I don't know if it's, well, I don't know. Universal seems, yeah, I mean, I think it has to do with Earth. Gravitation. Constant. It's universal here. Not in the whole galaxy, I don't think. Okay, so it says write the equation for the law of universal gravitation. Okay, so this varies directly, right? F, force, varies directly with, and we have our constant of variation right here, the universal gravitation constant, and the masses, M1 and M2, and they said it was divided by d squared. Okay. All right, so there it is. There's our equation. All right, now the next thing they said is estimate the universal gravitational constant. Use Earth and Sun facts given at the right. All right, so first what we're going to do is we're going to solve for g. So how am I going to do that? Well, I'm going to divide both sides by m1 and m2 and multiply both sides by d squared. So I'm going to end up with g, right, equals f d squared. Is that right? I'm going to multiply d squared on both sides, yet. And then I'm going to divide both sides by m1 and m2. I might be doing it different than what the book is doing. What are they doing? Oh, they're plugging all the numbers in first. Okay, well, either way, it's going to work out just fine. Okay, so now I'm going to do the next thing where g is going to equal, I'm going to plug in the numbers. So what's force going to be? Well, so we're doing all the stuff in scientific notation, and you can do it in scientific notation if you want. And I'm going to run out of space, and I'm going to multiply that by d squared. So it's times this, d squared, and d is 1.15, 1.50 times 10 to the 11th squared. So remember that means I'm squaring this and I'm squaring that. Divided by those M1 and M2, which, they're putting those in. So plug that in, M1 and M2. Okay, so that's 5.98 times 10 to the 24th times 1.99 times 10 to the 30th. Plug that into your calculator and crunch the whole thing out, and you should end up with the answer that they have given you right there in the book, which they're saying, then G is going to equal 6.67 times 10 to the negative 11. And look at this unit of measure. Newtons mass squared over, what is M? Oh, this is going to be kilograms squared somehow, I guess. No, what is the M2 then? Meters squared, that's right. So this is distance, that's right. Meters squared over kilograms squared. That's your unit of measure. All right, but all this you should be able to do right in directly in your calculator. So anyway, this section is a pretty easy, straightforward section, and it's getting us started on this chapter where we're going to be learning rational equations and functions. Rational equations, remember that's a fraction, so you're going to start learning about functions that are in the form, like polynomials that are in the form of fractions. It's a lot of fun. All right, that's it for today, and I'll catch up with you soon.